Okay, so let's start now. I hope my screen is visible and my audio is clear.
Yes, yes. Yes, sir.
Okay. So good evening, everyone. Welcome to third live session of mine for the course Design of Reinforced Concrete Structures offered by NPTEL. I am Harshit Agrawal, PMRF Research Scholar from IIT Bombay, and I will be conducting weekly live session for 12 weeks for this course. So, just to start with, what is this session all about? So, these are weekly interactive session which will happen every Tuesday from 6 p.m. to 8 p.m. till the course runs. And how we will interact in these session by answering the questions that I will ask in the chat box, by posting your questions in the chat box, or by raising hand, unmuting, and asking your queries. And how else you can clarify the doubts using the discussion forum of this course. The questions there will be addressed through the discussion forum only or in the next live session whenever possible. And with these live session you will be able to answer the graded assignments easily, and you will develop a further understanding about complex topics holistically. So I hope everyone are clear about the session. Now, in today's session, we will first have a look at what we discussed in the last live session that was for week 2 of this course. Just a quick glance. Then we will discuss week 3 content, starting a quick overview to limit state of collapse and flexure. Then we will talk about design versus analysis. Then we will look into some numerical based on singly reinforced beam design, and then we will discuss about doubly reinforced beam and will again look into some numerical, and finally we will talk about design of flanged beam in flexure. So in the last session we discussed about different components of a RC structure starting from footing, tie beam, columns, beams, and slab. Then we discussed how we actually design a RC structure. That is first slab, then beam, then column, and then footing. A top to bottom approach, which is opposite to how we construct a RC structure. Then we looked at some common terminologies related to design, neutral axis, where the net stress is zero, lever arm, that is the distance between net compressive and tension force, moment of resistance, which is offered by a component due to the couple of compression and tension to resist the external load. We also discussed about balanced under-enforced and over-enforced section of design, where the ideal one is balanced but not practical. So for safety, we provide under-enforced section. Then we discussed about working stress method, its assumption, stress strain block, equation, and some numerical also we saw. And finally, we discussed about limit state method of collapse and flexure. Again, we discussed about these assumptions, stress strain block, and equation. And finally, we also compared working stress method and limit state method from a design point of view. So I hope things were clear from last week, from last live session. You can also rewatch the session on YouTube, the link of which may be provided by you by the NEPTEL, NPTEL. So, moving ahead, we will talk about limit state of collapse in flexure. So, we saw several assumptions of limit state of collapse. What are those? First is plane section normal to the axis will remain plane after bending. Why this assumption is taken? So that the strain is directly proportional to the distance from neutral axis. The final conclusion of this assumption is this. Okay. The maximum strain in in concrete at the outermost compression fiber is taken as 0.0035. Okay, so this is a assumption of this design method. Now in last live session someone asked me why it is taken as 0.0035. So this is something that has been determined experimentally by the scientist who made the Indian standard, and this value is not constant. It can change. Maybe for high grade concrete, it can increase or decrease, or for low grade concrete, again it can increase or decrease. But generally, its range is from 0.003 to 0.004. So 0.0035 is generally taken for design purpose. Okay. The third assumption, that is tensile strength of concrete, is ignored. So we considered that the concrete can't take any tensile load, and all the tensile load will be taken by steel. The stress can be assumed as rectangular, parabolic, or any, which results in accurate estimation of strength. So we saw in working stress method, our limit was still elastic limit. So we had a straight line of stress strain curve. But in limit state of collapse, we are going till ultimate load. So we have a parabolic path after a straight line. So here we need to make the assumption of stress block such that we get an accurate strength estimation. The stresses in the reinforcement from the representative stress strain curve depending upon the grade of steel. So stress in the reinforcement we derive based on the grade of steel, and for design purpose we consider partial factor of safety of 1.15 for steel, and for concrete we consider 1.5. Okay. And the maximum allowable strain in the tensile reinforcement in the section of failure should not be less than 0.002 plus Fy upon 1.15 ES. So this is for limiting case. So when we define XU limiting, so in that cases we take this strain. Okay. Now based on these assumptions, we saw, and this is how stress strain curve looks like for a limit state method of design. So you can see here the strain diagram is linear. That was our assumption. The maximum strain, limiting value of strain for concrete and steel we know. And this is the stress block. So it will be straight initially and then a parabolic, and we have our reinforcement at this level. So below neutral axis, no load will be taken by concrete, no tensile load. So directly the steel will only take the tensile load, and this whole block will help us to calculate the compressive load of concrete. So based on these diagrams, we saw several relationships that can be derived for a limit state method of design. Just to summarize those relationships in a single page for better clarity, first we need to calculate the total compressive force or compressive strength. For that, we need compressive area. How we got? By taking total area of rectangle minus the area of excluded parabolic part. Okay, so this is how we got the total compression area. Once we got the compression area, we got the compressive force. Okay, now we need to know where this compressive force is acting. That was assumed to be at a distance k2x from the top fiber. And how we computed k2? By balancing the area movement. So we got k2 value as 0.416, or generally we take it as 0.42. Okay. Then we use the equilibrium of horizontal forces, that is tensile force will be equal to compressive force, and we derived one relationship where this can be used in several ways. Like if we want to design a balance section, we know x by d, so we can get ast, and if area of steel is given, we want to check for balance steel, we can do by calculating x by d. So this can be used when we are talking about balanced section design. Okay. How we got the limiting values of depth of neutral axis? From strain diagram. So we know the limiting value of strain. So from that, by using the similar triangle property, we got the limiting value of x by d. Okay, and x by d we can calculate from this. So both of these we can compare if you want to know whether we have under reinforced or over reinforced design. And finally, for calculating mu, if for calculating moment of resistance, if steel yields, we will use the first formula. And if concrete yields, we will use the second formula. Okay, so these were all the relationships that we saw how are derived in the last live session. Now, a little more into this, we need to understand two things: what is design and what is analysis. Okay, so what do we mean by design? Design is when we need to determine the design parameters of a section. What are those? What is the depth of the section, and what is the area of reinforcement we want to provide. So these are the parameters that we need for designing a section, and when we need to determine these parameters, we say we are designing a section. Okay, now what should be known if you want to design? Moment of resistance that the section is required to offer will be known, as well as grade of concrete and grade of steel. So when these things are known, we can determine the unknown design parameters, and this is known as design of a RC component. And what we mean by analysis? By analysis we mean how a section will perform. Okay, how we judge the performance of a section? By the moment of resistance of a section, by calculating the moment of resistance of a section, using which we comment whether the section is balanced, under reinforced, or over reinforced. Okay, now for knowing how the section will perform, we need to have design parameters. So here we will have width, depth, area of steel, and grade of concrete known to us. Okay, so when the design parameters are known, we do analysis to analyze the performance of section, and when the moment of resistance that the section will offer is known, we design the component for so that it can resist that moment of resistance. Okay, so I hope everyone are clear with the difference between design and analysis. Now let's look at one problem. Since in last live session we looked at a problem related to working stress method only, today we'll first look at a problem related to limit state of collapse and flexure. So this is the first numerical. A rectangular beam is to be simply supported on supports of width 230 mm. The clear span of the beam is 6 meter. The beam is to have a width of 300 mm. The characteristic superimposed load is 12 kilonewton per meter. Using M20 concrete and Fe415 steel, design the beam. Consider the self weight of the beam, assuming width to be unity. Okay, so this is a little complicated question than what you saw in the NPTEL discussion of week 2. Try to solve this question, else I will tell you the solution. So here, like first load is given. So superimposed load is given. You need to calculate the self weight also. When you will have the total weight, you can, since it is given that it is a simply supported beam, you can calculate the moment of resistance that it needs to offer, and that moment of resistance you will use to design the beam. So I have given you the initial hint. Try to solve the question. I will give you a couple of minutes, and then I will solve.
Hello, sir.
Yes.
So, what will be the depth of beam?
That is something that you need to assume. I will tell you how we assume depth of beam when it is not given in the question. Just wait for a while. No? There is one clause in IS 456. If the depth of beam is not given, then it is assumed as 1/12 to 1/15 of the span. So you know the span, it is 6 meter. So 1/12 of 6 meter or 1/15th times of 6 meter. Between this, you need to assume the depth of beam. I will tell you shortly, okay? So let's see the solution now, okay? So because we need to cover a lot of content, so let's move quickly. Now, what is given in the question? First is beam is simply supported on supports of with 230 mm. Okay. Second, clear span is given as 6 meter. Width of beam is given 300 mm. Superimposed load is given 12 kilonewton per meter. FCK we know 20 MPa and Fy we know 415 MPa. Okay. So how this beam is looking like, if I can show you. So this is a simply supported beam at the corners. Okay. So the clear span of the beam is given as 6 meter. Okay. And there will be some width of support also that we need to consider. Okay. So that is given as 230 mm. And there is continuous load acting over the beam, that is superimposed load. Okay. So here first using load we'll calculate the moment and then we will calculate the area of steel that is required, because that for that only we need to design the beam. Okay. But first the problem is we don't know the depth of the beam. Okay. So in such cases, when the depth of the beam is not given to you as per IS 456, depth depth of the beam can be taken as 1/12 to 1/15 times span. Okay. So which will be equal to 1/12 times 6,000, since it is given in meter. So we have converted into millimeter, time to 1/15 times 6,000. So what it will come out to be 500 to 400. Okay. So let's take small d as 400 mm. Okay, we will see if it is getting over enforced, then we can increase the depth of the beam also. But right now we will take d as 400 mm. Okay, now For calculating moment, we first need to also calculate the effective span. So we have been given clear span. What is the effective span? It will be nothing but clear span plus center to center distance of supports. Okay, okay. So this is like a general step of how effective span is calculated. So when we are calculating the net moment acting on the beam, so we go from the center of the support till the center of other support. So that will be clear span plus center to center distance of this support plus center to center distance of this support. Okay, edge to center distance. Okay, so in that total length, we assume that the load is acting. Okay, so what value it will be? It will be 6,000 plus 230 by 2 plus 230 by 2. So it will come out to be 6230, or we can say 6.23 meter. Okay, so this is our effective span. You need to remember this value. We'll see how we use this value later on. Okay, now we need to calculate moment, but before calculating the moment we need load. Okay, so superimposed load is given to us, that is 12 kilonewton per meter. But it is also given in the question that we need to consider the self weight of the beam. So how we can compute self weight? So self weight will be given by nothing but density into volume. Okay, what is the density of concrete? Generally, we take 20 kg per meter cube as the density of concrete. Okay, what is the volume? Length into breadth into height. Okay, so it will be point 0.3, that is the width of the beam given to us, times depth of the beam, that will be zero point 0.4, times length of the beam, that will be assumed as 1. Okay, for per unit we need to calculate weight per meter na, so that factor will take as 1. Okay, now here one mistake that we have done, this is the effective depth of the beam, but when we are calculating the weight of the beam we need the total depth. Okay, so here let's assume a cover of 50 mm. Okay, so if we are providing a cover of 50 mm, our total depth will become 450 mm. Okay. Sometimes you need to take assumptions if it is not given in the question. So let's assume a cover of 50 mm. So total depth will become 450 mm. So this factor will be 0.45. Okay. Now multiplying these value, we'll get the self weight of the beam, and that will be equal to, let me do the calculation, 3.375 kilonewton per meter. Okay, now what will be the total load then? So total load will be the sum of superimposed load plus self load. So 12 plus 3.375. So it will come out to be 15.375 kilonewton per meter. Now this is unfactored load, but when we are designing for limit state using limit state method, we need to factor the load also. So for ultimate load, we take a factor of 1.5. So factored load will be 1.5 times 15.375, which will come out to be 23.
Sir, sir, self-weight calculation, is it correct? Self-weight.
Yeah, you can check once, no?
Oh, sir, I'm getting something else.
Okay, let me check again.
6.7.
Okay, okay, my mistake. Wait.
So length will be 6 meter, right?
Huh. Actually, density of concrete we take as 25 kg per meter. You have mistakenly wrote as 20. Just correct that. Length, effective span we consider when we are calculating the moment. So right now we have calculated self weight per unit length. So we have taken 1 meter as the length right now. Okay. And density of concrete is generally assumed as 25 kg per meter cube, not 20. Okay, so what we will get factored load, it will come out to be 23.06 kilonewton per meter. Okay, now we know the load, this load that we were talking about, the continuous load acting on the simply supported beam. So, what will be the formula for bending moment? It will be WL square by 12, WL square by 8. This everyone knows. From basic structural analysis, we know what is the bending moment, maximum bending moment in the beam when a continuous load is acting on the beam. So we know all the values. So it will be 23.06 times 6.23 square upon 8. Okay. So everyone are clear with how we calculate the bending moment?
Factored load, please explain once again.
Okay, so this is the load that we calculated, the total load acting on the beam. But in the limit state method of design, we know that we also factor the load. So this is like the ultimate load which is acting. For safety factor, we multiply it by a load factor. So for ultimate load, we take a factor of 1.5. So this is how we got the factored load. Okay. So you saw like in working stress method, we only take a factor on stress, allowable stress, but in ultimate stress method, we factored load also that we saw in the first live session discussion. What all factors we take for dead load, live load, and everything. So this is the factor we take for dead load. So both of these are kind of dead load only right now. We don't have any live load acting on the structure. Okay. So multiplying these values, we'll get a bending moment of 111.88 or 878. Okay, kilonewton meter. Okay, so this is the bending moment for which we need to design the beam. Okay, so now we have the bending moment. Okay, so we first need to check we first need to check this bending moment with the limiting bending moment, limiting moment of resistance of our beam, so that we can know whether we have an under reinforced design or over reinforced design that we can continue with. Okay, so for fe 415 steel, what is XU? XU is 0.48D. So sometimes these values you can remember directly also, or else you can also always compute these values. So you have Fy value is 415, ES you know 2 into 10 to the power 5, that is for steel, and all the other values you know. So you will get epsilon SU, you know epsilon CU. So you can get XU by D value, the limiting value of depth of neutral axis. So I'm right now writing it directly, it is 0.48. So we know D is 400. So 4.48 times 400, it will come out to be 192 mm. Okay. So what will be MU limiting then? It will be nothing but 0.36 times fck times b xu d minus 0.42 xu. So 0.36 fck b xu d minus 0.42 xu. This relationship also we saw initially. Here we saw, okay, that d I have multiplied, so it is cancelling out. So the relationships come like this. Now substituting all the values, 0.36 into 20 into 300 into 192 into 400 minus 0.42 times 192. So mu limiting will come out to be, just wait a minute. So it will come out to be 132.445 kilonewton meter. Now we need to compare. So mu limiting is 132, around 132, and the bending moment that is acting on the beam right now, it is 111. So the section can be designed as a singly reinforced section. Okay, I will tell you why we did this. Like, you know the theory right now. You have read, you have seen the week 3 live sessions, so you know there are doubly reinforced section design also. So if my mu limiting would have been less than the bending moment, then we may have need to go for a doubly reinforced section design. But since right now the bending moment is lower than the mu limiting, then we can go for a singly reinforced design section. This is generally a check that we need to have always before designing a beam. Okay. Now it is a simple question. So we know mu is 111.878 kilonewton meter. We know B value, we know FCK, we know Fy, we know. So can anyone do the calculation for area of steel? Which formula we will use? This one. Okay. So we know Fy, we know mu, we know D, everything we know here. Okay. So right now I have the value. You can do the calculation on your own later on also. So the area of steel will come out to be 921.5 millimeter square. Okay. Now this is not the end of this question. When you got the area of steel, then you need to also tell the number and size of rebars. Okay. So generally, the size of rebar is assumed initially as 20 mm, and for for one rebar, the area will be pi r square. So you know the area of one rebar, you know the total area of reinforcement that you need to provide. So you can calculate the number of reinforcement that is needed. Okay, so that number of rebar will come out to be 3. Okay, so you can check both of these statements on your own later on. Try to do this calculation and you will get the size of rebar is 20 mm and number of rebars required is 3 mm. Okay, so everyone are clear with the solution. First, we calculated the depth of the beam. Since it was not given in the question, we assumed a cover. We got the total depth of the beam. Now, the clear span and the width of the support were given. So, we calculated the effective span, which came out to be 6.23 meter. Now, in the question, superimposed load was given and it was asked that to consider the self weight also. So, we calculated self weight. How? By multiplying density and volume. So, density of concrete is generally taken as 25 kg per meter cube, and volume we know. Okay, so we got the total load. Then we factored the total load because we are designing for limit state method of design in which we need to factor the load before designing for safety reasons. So we took the factor 1.5 and then we calculated the bending moment for a simply supported beam under continuous load. Once we calculated the bending moment, we first check with mu limiting. So mu limiting we calculated, we know the formulas. So we confirmed that the section can be designed as a singly reinforced section. And then for known bending moment B, D, FCK and FY, we calculated AST and we provided suitable number and size of rebars. Okay, everyone are clear with the solution?
Here we calculate the mu limit for steel, means ki not for concrete. I'm somewhat confused.
That won't be a problem. Mu limiting value will be the same, na? It won't change.
But in the numericals, we calculate mu for steel, mu for concrete, and
The
what will
limiting value will be same. You can calculate it by other formula also. You will get the same value. But mu then when you calculate, that is like steel or concrete. Anything can fail. This is for balance section. Okay. So in balance
yes.
section, we say both steel and concrete fail together. So that's why we can use any one of the formula. But when we are not making a balanced section, then steel can also fail first or concrete can also fail first, depending upon the section that we have designed. So that's why we calculate both mu from both steel and concrete in that case.
Sir,
Okay.
in this case, we have calculated for steel 111.878.
This is the bending moment that is acting on the beam. We have not calculated this value from steel or anything. This
Okay.
is due to the load that is acting on the beam.
Hello,
Hello. Yeah.
hello, hello. Sir, but we have not checked whether the our section is balanced section or over reinforced or under reinforced.
Right
And
now,
without knowing that, we are finding out that moment of resistance.
so for checking whether the section is under reinforced or over reinforced, we need to know the design parameters of the section. Na? We don't know the area of steel that we have that there is in the beam. Until we know the area of beam, then how we can check whether the section is under reinforced or over reinforced. So what you can do ahead, since you have provided this number of rebars and this size of rebar, you can back calculate and check whether section is under reinforced or over reinforced. You know the limiting value of moment. You can calculate the moment of resistance from the design
So
parameters that you have right now, and you can check again.
we
You
can
are
find out by comparing it with nominal shear stress. Like tau V is equals to V upon BD. And if it is less
what?
than tau C max, if we find out the nominal shear strength
Hmm.
and compare it with tau C max, then we can find out whether it is under reinforcement or over reinforcement.
But for commenting that, first you need to know na how much reinforcement you provided. See, there are two parts when we talk about.
Okay, yes, yes, yes,
We are
yes. I
right now
got it, got it.
designing a beam, not
Yes,
analyzing a
yes,
beam. So once we have
yes.
designed a beam, then we can analyze. Okay.
Okay, yes.
With the known values of AST, B, D, Fy, FCK, now you can back calculate. Check what mu you are now getting. Because you will see that the number of rebar, this value won't come out to be a whole number. It may come out to be 2.74 or 3.25 or something. So you need to take a approximation 3 or 4. And when you take a approximation, you need to check again whether your design is under enforced or over enforced. So right now, when we will provide 20 mm 3 rebars, you will see it would be an under enforced design also, which is safe to go forward with. Okay.
Okay, okay. Thank you.
And in that case, you can calculate moment of resistance using both concrete failure and steel failure. Okay, try to do that calculation. Everyone are clear now? Okay, so let's move ahead. So this was all about singly reinforced beam design in flexure. Okay. Now, what if in this question the bending moment that is acting on the beam would have been greater than the mu limiting? Okay. And I can't further increase the depth of the beam also. Okay, so in these cases, we need doubly reinforced beam design. Okay, so again, reiterating what I said, when the moment carrying capacity of a beam doesn't meet the design requirement for a singly reinforced beam, such that the construction depth can't be increased further, we go for a doubly reinforced beam design. Okay, so suppose my mu limiting value is 100 and the bending moment that is acting on the beam is 150. Okay, so since I can't go for a over reinforced design, I need to have an under reinforced or a balanced section of design, and I can't also further increase the depth of the beam due to some constraints, so I need to go for a doubly reinforced beam design. Okay, now this is one case where we go for doubly reinforced design, or there's one more case when we say that the bending moment can change signs. When it can happen when there is some moving load and the tension can occur both at top and bottom. So when the tension zone can be created at both top and bottom, we go for a doubly reinforced design. Okay, so for designing such section we need to consider some basic assumptions. We need to take into account some basic assumptions. What are these basic assumptions? RC section in bending fails in when the compression strain reaches the value of 0.0035. So this value we know. Limiting value is 0.0035. Okay. So this value is 0.0035. Okay. Plane section remains plane even after bending, which is again stating that stress strain is proportional to the distance from the neutral axis. And final point is stress at any point of steel and concrete can be computed by corresponding to the strain at that point in the stress strain graph of the material. Okay, so we'll see how this point is important now. Till now, we didn't saw any like much use of this point for a singly reinforced beam design, but in doubly reinforced beam design, we will see how this point becomes important. Okay, so let us understand these considerations that we have talked about by seeing the stress strain diagram of a doubly reinforced beam. So here you can see there are reinforcement at the bottom also and at the top also. Okay, so the strain diagram it will remain the same. 0.0035 is the ultimate limit of concrete that we consider here, and the ultimate strain is given by this formula. Now here I will have two values now. Okay, so the tensile force at the bottom will be due to these rebars only, but the compression force at the top will be due to both concrete and steel. Okay, so that's why we have two arrows right now for total force. This is due to concrete and this is due to compression force offered by steel. Concrete can't offer tensile force, but steel can offer compression force. So that we need to consider right now. Okay. So the total compression force for us will now become as CC plus CS. CC offered by concrete and CS offered by steel. And so since we have two compression forces, these two compression forces may act at a different level also. The CS will act at a depth d dash that will provide the effective cover that we are providing at the top, and CC will we know it acts at a distance 0.42 d. Okay, so if these two distance are difference, the lever arm value will also be different. Okay, so that's why the total moment of resistance now it is written as CC times ZC. ZC is the lever arm for concrete and ZS is the lever arm for steel. Okay, so this is how we write the stress equation. Okay, now for computing stress corresponding to a particular strain, we can refer to the material stress strain diagram. Okay, but now see, for concrete, we know stress will be this value only, 0.36 FCK. Okay, but see, here we have steel in the compression zone also. So this value may not be 0.002 now. Okay, this value will get from similar triangle property. It may come out to be a little different from 0.002. Okay, so this is how this assumptions comes into action. Stress at any point of steel and concrete can be computed by corresponding to the strain at that point. So if we know the strain that is acting at this level, that is the level of where the reinforcement is provided, the compression reinforcement. If we know the strain value here, then corresponding to the stress and strain diagram of steel, we can calculate the stress of steel. Okay, in the tension side, we generally take it as 0.87 Fy, but now in the compression side, we will have a different value depending upon the strain. Okay. Now, every time reading this curve may be a bit difficult to calculate the strain value of for compression steel. So we have a simplified table in SP16. So table F of SP16, it says that if we know the value of d dash by d dash is the value of the effective cover on the compression side and d is the effective depth. Okay, so if we know this value, we can directly say what will be the stress in the compression reinforcement. Okay, for different grade of steel. Okay, so this is how we calculate the stress in the compressive reinforcement. Okay, now we know the stress, we understand all these diagrams. Okay, the strain diagram, the stress diagram, and all these consideration that was taken into account earlier. So how we design doubly reinforced beam, that we don't know till now. So how the design is done? The design of doubly reinforced beam is done by dividing the beam into two parts. What are those two parts? First part is a singly reinforced beam. Okay, so we know our mu is greater than mu limiting. Okay, when we design W reinforced beam, when this is the condition. Okay, so what we do, we first take that part of mu which is equal to mu limiting. So mu can be written as mu1 plus mu2. Okay, my mu1 will be equal to mu limiting and my mu2 is the extra value, the extra moment that is acting on the beam. So first part is a singly reinforced beam which is a balanced section of design. So here mu1 is equal to mu limiting, and so for this we can design the beams as a balanced section. We can get the initial area of steel as ast1. Okay, now whatever the extra movement is acting on the beam that is causing it to be over reinforced, for that we'll calculate the ast2 and asc. Okay, but one question here, since we have provided steel in the tension side, why we are providing again a steel in the tension side and also in the compression side? Because here we have considered that the concrete and steel both are failing. Okay, so now in the second part we don't have any concrete, so the compression force here is offered by steel, and to balance the compression force that the steel is offering, we need a tension force also, so that will be offered by this reinforcement. Okay, so since the concrete has been used to balance steel in part 1, so we are having steel here in both directions so that we can maintain equilibrium. Okay. Will both of these area will be equal? No, because we saw in just right now that the strain value at both the level can be different. So if the strain value is different, the stress value will be different, and correspondingly the area of steel that we are calculating will be different. Okay. So this is how we do the calculations. Okay, everyone are clear with the theory? If everyone are clear with the theory, we'll see a numerical now.
So
Yes.
please repeat this one. Please repeat that MU for this
Okay.
uh,
So see.
ASC and
Hmm. So see here.
ASC and ASC.
Yeah, yeah, I understood. So why when we talk about doubly reinforced beam, when the moment that is acting on the beam is more than the limiting moment. Okay. So how to design such beams? We divide the beam into two parts. One part is the balance section that is taking the limiting moment, and the second part is the section which is taking the extra moment acting on the beam. So suppose if my mu limiting value is 100. Okay, and the mu which is acting on the beam is 150. So this first part I will design for 100 kilonewton meter only, and the second part I will design for 50 kilonewton meter. Okay, so how we'll design the first part? So if my mu is equal to mu limiting, we say that we are talking about a balanced design. So in this, we'll provide reinforcement such that both concrete and steel fail together. So that design we know for a singly reinforced beam how we design the section. Now my concrete has been used up to balance steel in the first part. So but I need a area of steel in the compression side also. How I will get? So I will get by taking steel in the tension side and steel in compression side such that they are in equilibrium and they are creating a couple strong enough to resist the extra moment that is acting on the beam. Is it clear now?
Yes, sir. Yes, sir.
Okay, so this couple that is created by the compression steel and the tension steel will resist the extra moment acting on the steel, and the first limiting moment part will be resisted by concrete and steel together as a singly reinforced beam. Okay, so let's see a numerical now. And these formulas I am not repeating because you know all the formula that was discussed in the lecture also. So AST2 is nothing but mu2 upon 0.87 Fy d minus d dash. So right now the lever arm will become d minus d dash. So this is d dash and this total is d. So my lever arm will become d minus d dash. So AST2 can easily calculate, and ASC again similar way. FSC d minus d dash into ASC will be equal to mu2. So this is nothing but just equating force into area is equal to moment. Okay. So let's see one numerical. So what this numerical is asking, design a doubly reinforced beam of width 230 mm and effective depth of 500 mm subjected to a factored moment of 200 kilonewton meter. Use M20 concrete and Fe415 steel. So I will give you a couple of minutes to try this question out on your own. So in the last question we discussed, na, initially we need to calculate the limiting moment so that we can know whether a design is doubly reinforced or singly reinforced. So start with it. You will find that the limiting moment is lower than 200. So that's why we are going with the doubly reinforced design. So then use the steps that we have discussed right now and try to design. Okay. I will wait for 5 minutes and then I will tell you the solution. Okay, so let's see the solution now. So in this question, what is given to us? Width of the beam is given, that is 230 mm. Effective depth D is given, 500 mm. Mu is given to us, 200 kilonewton meter. FCK is given, 20 MPa, and Fy is given, 415 MPa. Okay, so what will be the first step? Step 1 will be to check for mu limiting value. Okay, so calculating limiting moment of resistance. Here it is said that it is a designer doubly reinforced beam, so we know this moment will be more than the limiting moment, but still we'll check for limiting moment of resistance also. So how we'll get mu limiting? I'm audible, right? So I will get mu limiting 0.36 FCK B XU limiting times D minus 0.42 XU limiting. And what is the value of XU limiting? We saw in the last question also it is 0.48 times D. Okay, so it will come out to be 0.48 times 500, which will be equal to 240 mm. Okay, so XU limiting value we know, so it will be 0.36 times 20 times here one B will also come times 230 times 240 times 500 minus 0.42 times 240. So just do the calculation first. So this value will come out to be approximately 158.66 kilonewton meter. Okay, so you can see the moment acting on the beam is greater than the limiting moment of the beam. Okay, so this means that we need to go for a doubly reinforced design. Okay, so I will take a new slide. So my mu1 will be equal to mu limiting, which is 158.66 kilonewton meter, and my mu2 will be nothing but mu minus mu1. That will be approximately 413.42 kilonewton meter. Okay, 412. 413. Okay, you can do that correction. Okay, so we know for first part how much moment we need to design for, and for second part how much moment we need to design for. Okay, so now let's calculate AST1, that is for balance section of design. That is the first part of our beam. Okay, what I am talking here, this part. So when mu1 is equal to mu limiting, I will calculate the AST1. So I will calculate AST1 as 0.87 Fy times D minus 0.42 times XU limiting will be equal to mu1. or we can say mu limiting. Okay, so we know all the values. AST1. Okay, so AST1 will be nothing but 158.66 divided by 0.87 times 415 times 500 minus 0.42 times 240. Okay, so let's do the calculation. So this will come out to be around 1100.5 mm millimeter square. Okay, you can check the calculation on your own also. Okay, so this is AST1. So the area of steel required for balanced moment, for balancing the first part of the moment, that is mu1. Now for AST2 and ASC, we need an additional factor D dash. D dash we don't know. It is not given in the question. What is the depth of the reinforcement on the compression side? So there are two ways you can calculate D dash. Either using this testing diagram, or what you can do, huh, when d dash is generally not given in the question, we need to take an assumption. Okay, so right now we'll assume d dash as, that should be given in the question also, that is my fault. So assume d dash as 50 mm. Okay, so this should be given in the question. I will update the question. Assume d dash is equal to 50 mm. Okay, so I know d dash value. So I know the updated lever arm. Lever arm will now become d minus d dash. So I can calculate AST2 directly by this formula. Okay, AST2 is equal to mu2 upon 0.87 fy d minus d dash. So AST2 will be equal to mu2 upon 0.87 times fy d minus d dash. So it will come out to be, what is mu2? Mu2 is nothing but 413.42 divided by 0.87 times 415 times d is 400, 500, and d dash is 50. Okay, so just do the calculation.
Mu2 is 41.3.
Sorry, 41.3. And that was the confusion I was having. 41.34 kilonewton. So from this, now I'm getting correct here. AST2 will come out to be 254.18, or you can say 254.22 mm square. Okay, so total area of steel in tension side, it is AST1 plus AST2, which is 1100.5 plus 254.2, which is nothing but 1354.7 mm square. Okay, so what is this area? This area is the total reinforcement on the tension side. So this is the total reinforcement on the tension side. This plus this. Okay. Now we need to calculate the area on the compression side also. The area of steel on the compression side. How we'll do that? So we know mu2. So ASC will be nothing but mu2 divided by FSC times d minus d dash. And how we'll get the FSC value? We know d dash. So d dash by d, what is the ratio of d dash by d? 50 upon 500, which is 0.1. Okay, so from this SP16 for d dash by d equal to zero point 0.1 and Fy is equal to 4.415, my FSC value is 353 Newton per millimeter square. So either this you can remember directly for doing the calculation, or you can always go for using strain diagram by taking that similar triangle property and doing the calculation. So right now I'm using the direct calculation. So what I will have, 41.34 divided by 353 into 500 minus 50. So this will come out to be 260.2 millimeter square. Okay, so this is how we calculate, we design a doubly reinforced section. So now this is not over. You know the area of steel in the tension side, you know the area of steel in the compression side. So we need to provide adequate number and size of rebar so that you can meet these values. Okay. So just simply assume rebar. So generally in tension side we go for a 20 rebar, and in compression side you can go for a lesser diameter rebar also, 16 or 12 So just choose any one diameter and calculate the number of rebars. So this is how we design for both compression
Sir,
steel and tension steel.
sir, please once again explain FSC.
Okay. So see, um, the uh, we know that the strain from the strain diagram, we know the strain that is acting on the compression side won't be the same as the strain acting on the tension side. Okay, so the stress that this steel will offer will be corresponding the strain that is acting on the steel. Okay, so for that we need to calculate the compressive stress acting on the steel. Why, how we do that? By calculating the strain that is acting at this level, and then by using the stress strain curve of steel to calculate the stress value. So this SP16 table that I showed you, it directly gives us that value. So rather than going for like similar triangle property and calculating what is the strain acting here and then calculating the stress value, this table has simplified that calculation. How? You just need to know the d dash value and d value. So having both d dash and d, we can calculate what is the strain that is experienced by the steel on the compression side.
Sir, this table is giving D dash value, मतलब upper value 355. Suppose for 415, 355 is the D value and D dash is.
No, no, no. D dash by d is the ratio that we will get from the
Okay.
design. Like d dash by d is these values, zero point zero 0.05, zero point 0.1, 0.15, and zero point 0.2. So this is how you will get d dash by d ratio. And for
Okay.
these ratio and for this grade of steel, we can calculate the compression reinforcement.
Okay. Okay.
Okay, you can also check the value by calculating it for using similar triangle property. How you can do that? So suppose this is your stress strain curve. Now just drop a single line from here and extend it till here. Okay, so suppose this is the value that I require. Okay, so I will have two triangles here. So you can use this value. This is epsilon s that you know, okay, which will be equal to this value, you know, 0.0035. This small portion also, you know, it is nothing but 0.0035 minus epsilon that we need. Okay, and this depth, you know, d dash. Okay, so between this triangle and this bigger triangle, you can apply similar triangle property. So you will get d dash upon this value is equal to total depth d upon this value. So all the other values, you will get the value of epsilon. So you will get, since you know the strain from this stress strain graph, you can calculate the corresponding compression stress. So just to simplify that, all the calculation part, you can directly refer to this table for calculation. Is it clear now?
Yes, sir, clear.
Okay. So let's see the last part of the session now. Wait a minute. So we have talked about both singly reinforced beam design and doubly reinforced beam design. Now we'll talk about design of flanged sections. Okay, so what are flanged sections? These are the sections which are formed by two or more individual components. Okay, so what two or more individual components? These are the sections which are present at the interface. Okay, so suppose I have a beam and I have a column. So when these two sections will interact, it will form a flange section, which is known as L beam. Or suppose I have a beam and a slab over it. So these two are casted together only. So they together form a T beam kind of shape. So the section formed by the combination of two or more components is known as flange section. Okay. Now there are several considerations that need to be taken before designing a flange section. For now, the things that of our interest are, first, a slab shall be casted integrally with the web, and the web and the slab shall be effectively bound together in any other manner. So, what is web? Web is this small portion of weave, and this bigger portion is known as slab, or we can say flange. Okay, so when we cast reinforced concrete, we need to cast both slab and beam together such that they are acting as a single unit, so that they can form a flanged beam or T-shaped beam. Okay, so this is what is it is written in the first point. Okay, now when we are designing such sections, what is the width of the beam that we will take? Is it we will take from end to end? So till now we saw beams like this rectangular beam where width of the beam was this, but now my top part is a little extended. Okay, so in this case I take a width of the beam from somewhere from the sides. Okay, not from the edges but from a little distance inside from the side, and now it is calculated using these formulas. So these are something that you need to remember directly. There is no theoretical reason how these values came up. They did it experimentally. They estimated how to take the values and they calculated the values. So for these for this width of the beam, we are designing one flange beam. Okay, so these are some considerations that we need to take when we are designing a flange section. Now, based on the stress block, okay, so we saw for uh, limit state method of design, this is something how a stress block looks like. Okay, so based on the stress block, a flange section can be designed in three cases. Okay, there are three conditions now. First case is my neutral axis is lying within the flange. So this part is known as flange and this part is known as web. Okay. So first case is when my neutral axis is lying inside the flange. Second case is when my neutral axis is lying below the flange, but that the uniform stress plot is completely covering the flange. And the third case is when the neutral axis lies below the flange and flange is not uniformly stressed. Okay, we will see these cases one by one. For now, just remember that when we are designing a flange section, there can be three cases. First case is neutral axis lies within the flange, and the other two cases neutral axis lie below the flange. Okay. Now, how will judge which of these cases we are dealing with? How to judge? By calculating, by getting the values of df, total depth, and the depth of neutral axis. x. Okay, so for that also we need a limiting case. So suppose this is my flange and this is my web. What can be my limiting case? When my total df is this part. Okay, now for first case we can easily compute. If my x is greater than, if my x is less than df, we will say what is x? X is this length, the depth of neutral axis. Okay, if my x is less than df, we can say that the neutral axis is lying within the flange and we belong to case 1. But how to distinguish between case 2 and case 3? That is using, we need to take the boundary condition. So suppose my df is completely enclosing the uniform stress part. So we know, for uniform compression, till uniform till constant compression stress value, my strain value is varies from 0.002 to 0.0035. If you see this diagram, just I will go back. So when I talk about uniform stress, my strain is varying from 0.002 to 0.0035. So suppose I am assuming my df is this only, the limiting case. Okay. So how my stress diagram will look like? My strain diagram will look like this. So I know df is this part, d is the total depth, this is 0.335, 0.0035, this is 0.002. Okay, so if I assume my steel here, steel is generally taken as Fe415. So if I assume I am providing Fe415, so my epsilon SU will come out to be 0.004. So I can calculate the df by d value by a similar triangle property, and it will come out to be zero point 0.2. Okay, now if my x by d is greater than df by d. Okay, now if my df by d is less than zero point 0.2, then I can say that some part of that non-uniform stress will also come in the flange part. So I will belong to case 3. But if my df by d is greater than zero point 0.2, then I will say that my flange is uniformly stressed and the non-uniform part will come in the web. Okay, so this is how we distinguish between case 2 and case 3. Just go through these slides again, revisit the tutorial lecture audio, and you will get the clarity of what I am saying. You need to read couple of times so that you can understand. Try to derive this relation on your own. Try to check how DF is varying and how it is changing the stress block. Okay. Now we know how we can judge whether we are belonging to case 1, case 2, or case 3. But how to design for each case separately now. So let's look at each case now. So case 1 is when neutral axis lies within the flange. When it will happen? When my x is less than df. So now you can clearly see this is my x, this is my df. Okay, so if my x is less than df, my total compression part will lie in the flange only and the tension will be taken by the steel present in the web. Okay, so in this case, first how we'll get the value of x? X you can simply calculate by balancing the forces. Okay, by considering the balance section, you will get the value of x. You will know all these values, so you will get the value of x. You can compare x with df to check whether it is belonging to this case or not. Okay, so if this is the case, then I can directly write mu due to concrete failure as 0.36 FCK x by d 1 minus 0.42 x by d. This time b will be replaced by bf. Bf is this part. Okay, my width of beam will be width of flange. Okay, so this is how I will calculate moment of resistance due to concrete failure and due to steel failure. This is how I will calculate the value. Okay, so these are simple relationships. Again, I'm not iterating over how this relationship came, but you just need to check for x by df value so that you can know in which case you are belonging. Okay, so this is first case. Now suppose my x is greater than df. So my whole compression, this is my neutral axis and this is my df. Okay, so now there can be two cases. Either this constant stress part is completely covering the flange, or my constant stress part is not completely covering the flange. Okay, so if x is less greater than df and df by d is less than zero point 0.2, then we say that the neutral axis is lying in the flange and the flange is uniformly stressed. Okay, so when this will occur, what will happen? My mu1. So when in this case, what we do, we divide the flange into two components. One is this part, and the other is the remaining part, which is uniformly stressed. So this part above, this is under uniform stress. Okay, 0.45 FCK. Okay, so for these part, I will calculate mu2. For this part, I will calculate mu1, and I will write total mu is mu1 plus mu2. So mu1 we can simply write, we know the relationship due to concrete failure or steel failure, I can calculate mu1, and mu2 I can calculate because since this is totally concrete, so for concrete failure I can write mu2 as this. Okay, we know the width, we know this depth, and we know the FCK value. So I can simply write mu2 FCK into area. Okay. So calculating both for slab and for rectangle, this is the slab part and this is the rectangle part. I can write the total moment of resistance in case 2. And in case 3, what happens? This you can see here. Where is my mouse? Okay, you can see this non-uniform part is also coming in the flange portion now. Here, my non-uniform part was not coming in the flange. Okay, but now the non-uniform part is also coming in the flange. Okay, so in this case, when this case will occur when my x is greater than df and my df by d is greater than that critical value of zero point 0.2. Okay, so in this case, we need to do nothing else, just we need to replace bf by yf. Okay, so this is how we do that. Okay, this is just you need to remember why we are doing this is all like done experimentally. They got that this relationship you need to estimate so that you can take into account this non-uniformity. And once you calculate the value of yf, once you know that you belong to this case, you need to calculate the value of yf. You need to calculate the moment offered by rectangle by slab, and you get the total moment of resistance. Okay, so these are the three cases that we talk when we are talking about a design of flange section. So I know this was a lot to take. So just to summarize how to design a flange section, first we will know the parameters BW, BF, DF, and D, area of steel, grade of concrete, and clear cover. So first we will calculate X. How we'll calculate x? By considering balanced section of failures. So x I will calculate by assuming that the tensile failure and by assuming tensile failure and equating with the forces. Okay, so you will get the value of x. Now compare x and df. Okay, if my x is less than df, then I belong to case 1, where moment can be calculating due to both steel and concrete failure. If my x is greater than df, then I need to check the value of df by d. Okay, if my df by d is less than zero point 0.2, I am belonging to case 2. If my df by d is greater than zero point 0.2, I am belonging to case 3. Okay, and how to design for that, we will see in the next class now, how these design is done. But for now, just remember that there are three cases. There are two conditions to check for x comparison with df and df by d value. Okay, and based on those values, we check in which case we are belonging, and based on the case that we belong, we use the relationships for that. Is everyone clear with the design of flange section?
Sir, is in flange section we consider the doubly reinforced also, doubly
No,
reinforcement
no,
flange.
no. Right now, our discussion is limited to singly reinforced flange section. We will see later on in the course how doubly reinforced flange section can also be designed. But right now, try to understand a simple flange section design. Okay. We'll slowly complicate the thing, but for now we are talking only about singly reinforced flange section. Okay, so this was the theory behind flange section design. So this was all for this week. Just concluding what we discussed. So first we discussed limit state of collapse in flexure where we saw one numerical. Then we discussed when we need to go for a doubly reinforced design. That is when my mu is greater than mu limiting. And we saw stress strain block and its derivation, and we saw one numerical. And in the end, we discussed about flange section, what are flange section, different cases in flange section design, and how to analyze them. For that, we saw a simple flow chart of analysis. Okay, so this was all the discussion for this week. Thank you. If you have any doubts, you can ask. I will be there in the meet for 5 more minutes, else I will leave. Or if you have no doubts, you can leave the meeting.
How we will consider, how we will find out in a doubly reinforced beam that whether it is over reinforced or under reinforced?
In doubly reinforced beam, we don't need to check for that. Like the first part of the doubly reinforced beam, it is balance section. And the second part, we are balancing with the extra moment that is acting on the beam. So
Sir, if it is given that what is the steel in tension side, what is steel in compression side, then how
hmm.
we will know?
Okay, so if you know the steel in tension side and compression side, then first you will design this second part that you can do mu2 you can calculate. Okay, and then for the remaining steel you will calculate mu1. If your mu1 is still more than mu limiting, then you can say that it is an over reinforced design. You need to backtrack when you're checking for over reinforcement. So ASC and AST2 are under equilibrium. Okay, you know the value of ASC. Okay,
Yes,
you can
yes,
get the value of mu2.
yes,
Okay, you know mu2, then you can calculate AST2.
yes.
If you know AST2, you will calculate, you know AST1 because you know the total area of steel in tension side.
Mm.
For
Yes.
AST1, calculate mu1, assuming
Okay.
both steel and concrete failure. If that value is more than mu limiting, then it is a over reinforced design of doubly reinforced section. You
Okay,
got
thank you, sir.
okay.
Hello,
Yeah.
hello.
Yes. Yes.
So my question is that in singly reinforced concrete beam,
Yeah.
while we found that our section is over reinforced,
Hmm.
and when we find that movement of resistance, then in that case we consider xu is equals to xu limit.
When we are talking about balance section.
Yes.
Okay.
If the section is over reinforced, then we consider xu is equals to xu limit, right?
No. 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 When the section we don't design a over reinforced section. We first check if my section is under reinforced or balanced. If my section is over reinforced, then we need to go for a doubly reinforced design. That is why we talk about doubly reinforced design. No? So
Okay.
in this
Okay.
question, what we did, we calculated mu that is acting on the beam from due to external load.
Hmm.
Then we calculating the limiting moment of resistance. If my bending moment would have been greater than the limiting moment of resistance, then we could not have designed a singly reinforced beam. Okay. If it is over reinforced, then we won't design. And
Okay.
finally, when you will provide area of steel, na, you need to again back
Hmm.
check what is the limiting moment of resistance. Okay, or what
Okay.
is the moment of
Yes.
resistance? If it is more than limiting moment of resistance, then you have provided wrong number of reinforcements.
Okay.
So if there are no further doubts, we will end the session now. Okay, thank you.